not able to attend. And we're going to pick our discussion back up with random variables. We were in the midst of talking about the exponential probability distribution at the end of the last class, and that's where I want to pick up this morning. We had begun looking at the first example, but we were unable to finish it. So that's where I want to pick up. And I have copied this example onto a Word document so that we can talk about it. But I think it would help if I would share the screen. So let me do that. Okay. So the question that we were looking at, again, we were focusing on the exponential distribution. And the question or the example we were looking at said, on the average, a certain computer lasts 10 years. The length of time the computer part lasts is exponentially distributed. And then it asks you some preliminary questions about what is the mean, the standard deviation, and the decay parameter for that problem. I had mentioned to you that typically with these particular type problems, they will identify for you whether, what type distribution you have. In the uniform distribution problems that we looked at previously, it would say uniformly distributed. Typically with the exponential distributed, again, they're also going to tell you that. If not, remember that exponentially distributed usually has to do with something usually related to time and how long something's going to last from a particular point. And we talked about that in last class. I also mentioned to you that in the last class, and let me just back up to that portion of the PowerPoint for some of you maybe who missed it. But typically it will state that it is an exponential distribution and it gives you the average or the mean. We also talked about that, the standard deviation is equal to the mean, and you have a important measurement called the decay parameter, which is represented by a lowercase m and is equal to 1 divided by the mean, or the reciprocal of the mean. I also had provided you with the formulas. This is a hand calculation or a calculator calculation that we do. It is not something where you'll be using Minitab. And so there's one formula if you are talking about an area to the left, which would typically be a less than, and there is a different formula if you're talking about areas to the right, which is a greater than, and we're going to look at how to use those formulas. I also encouraged you last class, and I'll remind you here, you may want to make yourself a formula sheet, because I've given you formulas for the uniform distribution. I've also given you, I've given you the formulas here for the exponential. And so you may want to put together a formula sheet, so you'll have that when you are working through the quiz and also working through the midterm. Okay, so let's go back to this question. So it asks us, first of all, what is the mean? And again, the mean is given to us in the problem. It uses the word average, but it says on average, a certain computer part lasts 10 years. And so our mean, which is represented by the Greek letter mu, is 10. The standard deviation for the exponentially distributed variable, remember the mean is equal to the standard deviation. And so for this problem, the standard deviation would also be 10. The decay parameter is 1 divided by the mean. So we would have 1 divided by 10, which is 1/10. I would write it as a decimal. You could leave it as a fraction, but most people do not like to use fractions, so a decimal is okay. So then the first question, which I think we actually got to work through the other day, but again, I wanted to kind of pick back up with it, said, what is the probability that a computer part lasts more than 7 years? Now, I'm not going to draw it to scale by any stretch of the imagination, but again, it may help you to kind of visualize what's going on here. Okay, and an exponential distribution looks something like this. Okay, and so you got to figure it runs 0 to on average of 10. If I put the mean out here, it could last longer than 10. I guess I should put the mean in the middle, sorry, which is 10. But it could keep on going, and technically, because it is a continuous probability distribution, technically, theoretically, this could go on and on forever and ever to infinity. And so this question says, what's the probability the computer part lasts more than 7 years? So if I kind of guesstimate where 7 is on my number scale and think more than is greater and would be the region to the right. The reason I drew this picture is because I want you to realize that this is to the right, which helps you recognize or identify the formula that you need to use. If you go back to the PowerPoint and look at those formulas, the formula for to the right is this one here. F of x equals e to the negative mx. Okay, so the picture helps you visualize it. It's not a requirement to solve the problem, but again, it may help you recognize that you need to use this formula. F of x equals e to the negative mx power. Now, e, remember, is the natural number. It's estimated to be 2.72, similar to pi, if you're familiar with pi from algebra. But our calculator has that built in, or if you have a scientific calculator, it'll have it built in and it'll do the work for us. So once I have identified the formula that I need, then it becomes a matter of substitution. So I have f of x. I'm actually doing f at 7 because it says more than 7. So we have e to the negative. M is our decay parameter, which we determined to be 1/10. And my value that I'm interested in, again, in this problem is 7. So that simplifies to e to the negative 7/10. 1/10 times 7 is 7/10, and it is negative. And then I can go out to my calculator, and I'm going to pull mine up. I do use, because it's what I have on my computer, a TI-84 Plus. But if you can use a simpler calculator, primarily you need hopefully to have a scientific one that would have the E on it. On mine, it's on the above the LN button, which is next to the 4. In blue, you see E to the X. So I'm going to press the blue second button and then LN, and the little E comes up on my screen. And then I want to enter negative 0.7. Okay, because I did that calculation in my head. Then I'm going to hit enter. And let me get this out of the way so you can see it. So we get 0.496585. Okay, so let me go back over here. So we get oh goodness, I forgot what it was. 0.4965 We typically round to 4 decimal places, and we talked about rounding a little bit last week as well. The 4th place here has a 5. Next door is the 8. The 8 is going to bump it. So this would be approximately 0.4966. And that would be the answer that I would want to use or enter into the answer blank in the quiz or the midterm. Okay, questions? I believe we also looked at this second question, but again, I want to review it again. It says, on the average, how long would five computer parts last if they are used one after the other? So you have your computer part 1, you have computer part 2, you have computer part 3, computer part 4, and computer part 5. It tells us in the problem, in the initial scenario, that on the average, that the computer part lasts 10 years. So we would anticipate on average, the first part would last 10 years. As soon as it quits working, I'm going to put in the second part, and I would anticipate that it lasts 10 years. As soon as it stops working, I'm going to put in the third part and anticipate it works for 10 years. When it stops, I'm going to put in the fourth part and anticipate it works for 10 years. And then when it stops, I'm going to put in the fifth part and anticipate that it works for 10 years. And when it stops, I guess I'm out of luck or I have to order a new part. Okay, so each computer part lasts an average of 10 years. And so if I add these together, does somebody have a question?
Yeah, I do. I'm sorry, I had to step away for a minute. Can you explain again where that 10 is coming from?
Okay, the 10 is the average.
Oh, okay, gotcha.
Okay, that comes in the original because the original problem says on average, a certain computer part lasts 10 years. And the clue in the question to use that 10 is, again, it says on the average. So again, the average or the mean is 10. And so 10
Okay, thank you.
plus itself 5 times gives me 50. So I would anticipate if I have 5 computer parts that they would last for a period of 50 years. All right. I want to skip the third question for a minute and come back to it. Okay, because it's a little bit different. I want to jump down to the fourth question. The fourth question says, what is the probability that a computer part lasts between 9 and 11? So our question here is asking between 9 years and 11 years. Now, a couple things I want to point out. If you go back and look at the formulas that I gave you, you have a formula for area to the left, and you have a formula for area to the right. Neither of those talk about between. So it actually requires us to do a couple of calculations. And again, I want to try to help you see this visually on a graph to kind of help you hopefully understand what we're doing. Again, we have our continuous probability distribution, and theoretically it does go to infinity. The mean would be 10 because that's what we're told, and you have the exponential distribution. Again, it's by no means drawn to scale. In this question, it asks us how long will the computer part last, or what's the probability it lasts between 9 and 11. Okay, so this is, and I'm actually looking for this area or this region here, but I don't have a direct formula for calculating a between. Okay. So here's what we have to do. To get the between, we're going to calculate the left minus the right. Okay, let me see if I can show it to you. If I calculate the area to the left of 11, which takes me all the way back down to 0. Okay, so this is left for 11. And then I calculate the area to the right of 9. And I subtract them. What's going to be left is the overlap, which is the region that I want. Okay, so it's a little bit trickier and requires you to do 2 calculations. Now, I would tell you to treat it as 3 problems in one. We're going to calculate the left as problem number 1. We're going to calculate the right as problem number 2, and then subtract the 2 answers as part of problem number 3. If you're really efficient with the calculator, you could do it all in one step, but just to be careful. So we want to do the left of 11. Okay, so the formula for figuring the left, the area to the left, is 1 minus e to the negative mx. That's the formula that's given to you on the PowerPoint. Okay, that you'll need to have on a formula sheet next to you. I don't even have them memorized myself. I've got me a little note sheet over here to the left of my computer. Okay, so I'm going to perform those calculations. I'm going to get a different color. So I would have f of 11. So I have 1 minus e to the negative. Our decay parameter, which is the m, was 1/10 times 11. So I have 1 minus e to the negative 1.1. Now, if you have trouble doing that calculation in your head, guys, please go over to the calculator and do negative 0.1 times 11. Okay, if you struggle with the calculations, don't make an error. Okay, use the resources. So then I'm going to do 1 whole minus, get my e, to the negative 1.1, and I'm going to enter. Okay, so I get, and let me write it down real quick where I can see it, 0.6671289163. Now, guys, your calculator will store it, and if you want to, store it, you can do that and then bring it back up later. I don't want to get too technical on you, but calculators will have a memory. So I have 0.6671289163. Okay, so that's the value for left of 11. Then I need to go back.
Do you want to keep it that full number, or do you round it?
Abigail, to the very end, I'm going to keep that whole number. Okay. And then at the end, I'll round it. I don't want to round too many times before I get to the final answer. So I'm going to carry out that whole decimal. Okay, so right of 9, okay, because I need to figure out going up from 9. So the formula for right of 9 is, goodness, I've lost my mouse. F of x equals e to the negative mx. Okay, so I'm doing f at 9 because that was the value that we were asked to find. So I have e to the negative. Again, my decay parameter is 1/10 times 9. So that gives me e to the negative 9/10. I'm going to go out to my calculator and calculate that value. So second e negative 0.9 gives me 0.4065696597. Okay, and again, I do want to carry those decimal places out till I get to the last step. So this one equals 0.4065696597. So there's my answer for 9. And then to get my final answer, I need to subtract these two numbers. So I'm going to go back to my calculator. Okay, so I'm going to make you a little note here. Let me see if I can make some space here. Whoops. Nope. Okay, let me see if I can scroll back up. We want to do f at 9, or excuse me, f of 11. We're going to do f11 minus f of 9. So I'm going back to my calculator, and I'm going to have 0.66712896163. That's f of 11 minus the other decimal, and I can pop it in and enter, and I get 0.2605. Write it down, 26055925566. Okay, so if I carry all those decimal places, when I get these two subtracted, we get 0.2605592566. And that corresponds to this magenta purpley looking color there. Again, we typically round to 4 places. The fourth place has a 5. Next door is a 5, so it's going to bump it up. So we would round and have 2606, 0.2606. So approximately 26% of there's a 26% probability that that computer part lasts between 9 and 11 years. But that one's not, because of the between, it's not as straightforward. You have to figure the left region, the right region, and then subtract to the two. Questions before we go back to the third one? Okay, the third question in that same scenario, it says 80% of computer parts last at most how long? Now this question is different because they've actually given you the percentage to start with. It's kind of like you're starting with the answer and you're trying to backtrack to the X value. Okay, so again, let me see if I can show this to you visually. Again, we know that it's continuous, so it goes from 0 to feasibly infinity. The mean is 10. You have that exponential distribution. Okay, and it says 80%. So it's kind of like I already know it lasts at most. Okay, so I'm just going to make a mark here. So between here and the end, this region that we have here corresponds to the 80%, which we write as a decimal. Okay, I'll just make a note there to show that it. So we already know the percentage. What we want to know is what X value, okay, how long is that going to be? So we're looking for the X. And we could do the algebra, okay? I could use the same formula because I'm looking for the area to the left, okay? Yeah, Abigail?
I'm a little bit confused. Like, how do you know that that area that you outlined in that yellow, how do you know that is the 80%?
Because the problem tells me it's 80%. And my
Well,
graph is probably not drawn to scale by any stretch of the imagination. But I know
how do
that
you
the
know, I guess, that
mean,
the X comes after the 10?
because the
I guess is what
mean
I'm trying to.
is the middle, which is 50%.
Okay, gotcha.
The mean, remember, is a measure of center. And so it would be in the middle. So I'm anticipating that it would be more than the mean.
Okay,
I
that makes sense.
could be wrong, but again, I'm not, the picture itself is probably may not be drawn correctly, but I'm trying to help you visualize what I'm talking about. Again,
Yeah, that makes sense now.
I could take this and I'm going to show it to you just so you think. This would be like F of X, and this is to the left. So we would have the formula 1 minus E to the negative mx. Well, I know that this F of X is the 80%. Okay. That equals 1 minus E. And I know that my decay parameter is 1/10, and then the X. So there's the equation in algebra that you would have to try to solve to figure this problem. Okay. I'm going to give you a formula that's going to help, that's just going to let you plug and chug. Okay. I can show you the algebra if you want to see it, or if anybody wants to see it, I'll be happy to show you. But it's probably more than you maybe want to try to remember from algebra at this point. So the formula for figuring the X, they refer to it as K, okay, is the natural log of 1 minus the area, which is your percentage, divided by negative m. Okay, if I do the algebra, that's how it's going to play out here in a few minutes if I did the algebra. Okay, so instead of calling it X, they call it K. Not a big deal. Okay, I can put the K back up here. And it's the natural log of 1 minus the area. The area corresponds to the percentage, because remember, area equals the probability. Probability is a percentage divided by negative m. So if I plug and chug into this formula, I'm going to have, I need the natural log of 1 minus the 80% divided by negative 1/10, because my decay parameter we determined early on was 1/10. Okay, so I'm going to do a little bit of the math here. So I have the natural log of 20% divided by negative 1/10. And then I've got to use my calculator. Okay, so I'm going out to my calculator. Let me clear all this off. We're going to use the natural log button, which on my calculator is on the left-hand side near the number 4. It has ln. So I put ln of the 20%. I did that calculation in my head. And then I'm going to divide that by negative 1/10, because 1/10 was my decay parameter. So that gives me 16.0943. Okay, so 80% of the time, the computer part is going to last approximately 16 years. Okay, this is approximately 16 0.09, and you have more decimal places out there. So 80% of the time, my computer part would last at most 16 years. Okay, 80% of the time, the computer part lasts at most 16 years. Remember, 10 years is the average, but it could last longer, as indicated here, or it might last less. But we're talking 80%. And again, remember, the mean is a measure of center, so we anticipate that being about 50%. Guys, you need to make sure that you write this formula down. Okay, let's look at, there is a second example on that PowerPoint, and I want to go ahead and look at it so that you have a variety to consider as you're working through quiz 3. So the second example on the PowerPoint for continuous probability distribution says, suppose the distance in miles that people are willing to commute to work is exponentially distributed with an average distance of 20 miles. Now, again, I would strongly encourage you guys, please take the time to read the question fully from start to finish, because again, in these problems, it's going to identify for you what type distribution you have, which then should lead you to your formula sheet to say, okay, I'm going to use these formulas for exponential, or I'm going to use these formulas for uniform, or later today we're going to get into the normal distribution. And then it says with an average distance of 20 miles. So again, in these scenarios, some, if not all, of the information that you need for working the problems are provided, such as the mean and possibly the standard deviation. And then it asks you the preliminary questions again. It says, what is the mean? Remember, the mean is given in the problem. It uses the word average. So the mean is 20. The standard deviation is actually also given to you because for the exponential, the mean is equal to the standard deviation. So the standard deviation for this problem is also 20. The decay parameter is 1 divided by the mean. So in this case, that would be 1 divided by 20. And again, I'm going to convert that to a decimal just for easier use. 1 divided by 20 is 0.05. Now again, you should have all of those formulas written down. So then the first question says, what is the probability that a person is willing to commute more than 25? And again, it's important that you pay attention to those phrases, more than 25 miles. Now, even without drawing the picture is not required, but again, just to help you visualize this, again, 0, we know it could go on forever. The mean is 20, and we have our exponential distribution. It says more than 25. So 25, I hope you do realize, is greater than 20. And we want to be more than that. Again, this little simple sketch, not drawn to scale or anything like that, helps you to realize this is going to be to the right, which again, hopefully triggers in your mind to go back to your formula sheet and pick up the formula you need, which is f of x equals e to the negative mx. And so then I'm going to do the substitution. I'm figuring for a value of 25. So I have e to the negative 500ths, that was our decay parameter, times 25, which is the value given in the problem. I can't do that calculation that quickly in my head. So negative 0.05 times 25 is negative 1.25. So this becomes e to the negative 1.25. And then I'm going to use my calculator. Whoops, wrong place. Again, the e to the x is above the ln button in blue. So it's the second e to the x. My exponent is negative 1.25, and I enter, and I get 0.2865 is in the fourth place. 0 is next door. It doesn't bump it. So my answer is 0.2865. So approximately 29% of people are willing to commute more than 25 miles. Or there's a 29% chance they're willing. Excuse me. Okay, then the next question says, what is the probability? I left out a word there, sorry. What is the probability that a person is willing to commute less than 15 miles? Okay, again, it is extremely important that you pay attention to the words. Okay, again, if I draw a rough sketch here, 0 minus 20. My point of interest here is 15, which is less than 20, and we want to be less than that. So I'm looking at this region to the left. Again, hopefully that makes you visualize or recognize it's to the left, which again then helps me to identify the formula we need, which would be f of x equals 1 minus e to the negative mx. We are figuring for 15, so we're going to do f of 15. So we have 1 minus e to the negative 0.05, that's our decay parameter, times 15. Okay, so I have 1 minus e. Again, I can't do that calculation that quickly in my head. So 0.05 times 15 equals 0.75. I did forget my negative there. So negative 0.75. So then I'm ready to do the calculations. 1 whole minus e to the negative 0.75. We enter. We get 0.5276. 6 is in the fourth place. 3 is next door. It doesn't bump it. So I get 0.5276. Okay, so this is approximately 0.5276. So there is about a 53% chance that a person is willing to commute less than 15 miles to work. About a 53% chance that a person is willing to commute less than 15 miles. Okay, and then we come back to kind of that inverse problem. This one says 90% of people are willing to commute at most how far? So again, if you visualize this, again, remember the mean is the measure of center. So it's roughly at 50%. So 90% is going to be somewhere above the mean. So this shaded area here is 90%, which as a decimal is 0.90. Using the formula, we're going to find what they call K. K equals the natural log of 1 minus the area divided by negative m. And if once you have the formula, honestly, it becomes a plug and chug. So we have K equals the natural log of 1 minus the 90% divided by negative 5/100, because that's the decay parameter. So I have the natural log of 1/10 or 10% over negative 0.05. And I'm going to use my calculator. Natural log of the 10% divided by negative 0.05. Enter. And I get 46.05. Okay, so this is approximately 46.05. So 90% of people are willing to commute at most 46 miles to work. So there are people who are willing to commute up to 46 miles to work. Questions? Okay, that does two things for us. Okay, that finishes the discussion of exponential functions that was remaining from last week. You are now able to do quiz 3, which is due on Sunday. It also finishes module 1. Okay, if you go back into the course and look at module 1, we have covered data and visualization. We've covered descriptive statistics, missing data, and and outliers. And then we've spent the last couple of classes talking about random variables. We covered discrete random variables, and we focused on kind of a general discrete probability distribution and the binomial. We then moved on to continuous probability distributions, and we have focused on uniform and exponential. But we're really not quite finished talking about random variables, because in the beginning of module 2, we're going to talk about the normal distribution. And in the introduction to module 2, it says that we will continue that. The most important of all probability distributions is the normal distribution, which is bell-shaped and symmetric. You see the bell curve in almost all disciplines. Some of the included disciplines are psychology, business, economics, the sciences, nursing, and of course, mathematics. Some of your instructors may use the normal distribution to help determine your grade, aka grading on the curve, and the normal distribution is an extremely important concept that will be used throughout the remainder of the course. So we're not totally leaving the discussion of random variables. The first lesson in Module 2 on normal distribution is going to address normal distribution. I do want to show you something that I've done. I did it for the random variable lesson, and I've also done it for the normal distribution. Already embedded in the course were some PowerPoints, but I have updated those, and those are the ones that I am using during our class discussion. And so I have posted those in the same location, but I've indicated updated PowerPoints, new ones by Mrs. Ralston. Okay, so if you're trying to follow the video, okay, you may want to use this particular PowerPoint. It's not that the others are not good, it's just that I kind of drill it down and get to the nitty-gritty in the ones that I'm updating. Questions? All right, let's see how far we can get in our discussion of normal probability distribution. And I do realize if you look at the course schedule, I'm a little bit ahead of schedule, okay? Not necessarily a bad thing. So we're going to keep moving forward. So let's talk about the normal probability distribution and its uses. We talked earlier about what a probability distribution is and how that it helps us to describe what probably theoretically should happen as opposed to what actually happened when we collected the data. We also talked about how that a lot of decisions are made in business, insurance, and other real life situations by assigning a probability to all the possible outcomes. And these are just some examples, kind of that scenario in business for worst case, best case, likely case, forecasting sales, risk evaluations, rates of returns on stocks, perhaps, standardized test scores, lifespans of consumable items. We just kind of talked about that with the exponential, with light bulbs, batteries, tires, even birth weights and heights. So the normal distribution is the new one that we're going to consider. It is a continuous probability distribution. Okay, so the normal distribution is continuous, meaning that the curve is smooth, it is connected with no gaps. It also means that our distribution can run from negative infinity all the way up to positive infinity. Technically, theoretically, it could go on forever and ever in both directions, whether it's negative or positive. One of the key characteristics about the normal distribution is that it is symmetric. Symmetric means that your left side and your right side are mirror images of one another. Let me see, I have to kind of get out of this little part of it, but let me see if I can kind of draw what you would think of when you think of a normal distribution, or when we draw one. Okay, normally we only draw one axis. We draw the horizontal x-axis, and then you have kind of that very nice bell-shaped curve. And notice how when I drew it that I didn't have to lift my pencil. Again, that gives us that sense of being continuous. It is symmetric. If you could imagine a line in the middle of the graph that we would fold across, okay, you know, like fold on the dotted line, so to speak, you couldn't tell the left side from the right side. What we learned earlier is that in a symmetric distribution, our mean, our median, and our mode are all virtually the same value. And for a normal distribution, you do only have one mode. We typically label this line with the mean. The reason we label it with the mean, there's really two reasons. One is that the mean, remember, is the most important of the measures of center, and it uses all of the data values in its calculation. But also it is one of the parameters, one of the measurements that we use to actually calculate the shape of that distribution. It is bell-shaped, meaning that the majority of your data is kind of in the middle. If you want to think about how it is kind of clumped together, most of your data is going to be within the center, and you have very little on either end. It kind of tapers off as you get out to those higher values on the right or the lower values on the left. Those ends of the curve we tend to call the tails. The shape of your distribution is determined by two different parameters. It's determined by the population mean and the population standard deviation. Now, you don't have to know this, but the formula that you would use to model that normal distribution looks like this. And guys, it is super duper messy. It is E raised to the minus X minus the mean squared divided by, I gotta make sure I get it right, 2 times the standard deviation squared. And then that whole thing is divided by the standard deviation times the square root of 2 pi. That's the formula. Just like in algebra, you have the equation of a line might be f of x equals mx plus b, or you have the quadratic, which is f of x equals ax squared plus bx plus c. This is the formula for that normal distribution curve, and it is yucky. But again, one little quick note that I can show you here is if you look at all these numbers, the value for E is constant. It's always 2.72. The number 2 is constant because it's just plain old 2. Same thing here. Pi is also a constant. It's always 3.14. And if I take the square root, it's going to be constant. So if you look at all of the constants here, the only thing that can change from problem to problem is your mean and the standard deviation. And I can actually use any number that I can think of for the mean. And I can use any number that I can think of for the standard deviation except 0. The standard deviation cannot be 0 because in this crazy formula, you have it in the denominator of a fraction in 2 different places. And if you'll remember from regular math, you can never have 0 in the denominator of a fraction. So I can choose any number that I want for the mean and any number that I want for the standard deviation except 0. So that means I have an infinite number. There are an infinite number of normal distributions. And we're going to see that, I think, in a minute on one of our slides. Two other characteristics that we talked about specifically in relationship to the normal distribution, or not normal distribution, but continuous. And we'll come back to that in a minute because here are some graphs. Look, these are 3 different normal distributions. The red one has a mean of 0 and a standard deviation of 1. The green one has a mean of 2.5 and a standard or a variance of 4. excuse me, not standard deviation. So there's 3 different ones just right there. But guys, again, think about it. I can use any mean, any value for the mean, and any value for the standard deviation, except 0, in any combination. So there are an infinite number of normal probability distributions. This is just an example of 3. Now, here's what I was getting to. 2 of the characteristics that we talked about specifically in relationship to the continuous probability distribution is that the total area under the curve was equal to 1 or 100%. That also holds true for the normal distribution. And again, that seems odd because that normal distribution, as it moves out towards negative infinity and positive infinity, keeps going forever and ever. It never actually touches that horizontal x-axis. And I mentioned to you previously that to prove that to you, we have to do some calculus. But it all goes back to the fact that the sum of the probabilities for all the possible events is 1. So when we talk about a normal distribution, okay, you have to know 2 things about that normal distribution. Well, 3 things really. You have to know that it's normal. You have to know the mean, and you have to know the standard deviation. And sometimes they'll write it in this kind of fancy dancy notation. This says that the variable x approximates a normal distribution with a mean and a standard deviation, and they'll give you numbers there. Okay, so you may see this notation in some of the problems. Okay, the x is your variable, the n, which hopefully makes sense, stands for normal. Okay, instead of writing it out in words, that's just kind of the mathematical shorthand. But guys, you have to know those 3 things. You have to know it's normal, you have to know the standard deviation, and you have to know the mean. Okay, just some examples of using normal probability distributions where you can use it to model things. And I'm not going to read a lot of this, but you can do it for looking at the height of a population, which might be done by, say, the CDC or the National Health Organization. Within the stock market, looking at the returns within a stock market, your predictions follow a normal distribution. Income distribution, if you're thinking about the economy. Birth weights of babies follow a normal distribution. Inventory forecasting. Okay, notice that even this one here for this inventory forecasting, it kind of looks a little weird, but it still has that basic normal distribution shape. I mean, it doesn't necessarily have to be perfect. And when you're modeling with statistics, it's not going to necessarily be a perfect model. Blood pressure is an example where we can also model forecasting or model using a normal probability distribution. Milk productions of cows, how much milk a cow produces each day. Even we can monitor climate change because temperatures tend to follow a normal distribution. So again, there are a variety of uses across a variety of fields where we use the normal probability distribution. Just a little bit of history. Before we had calculators and computers to help us, to solve a normal distribution problem was very tedious, and some might say complicated, because you had to perform calculus. You had to take the integral of this crazy looking formula that I showed you just a minute ago and look at, okay, from point A to point B. And so, you know, it was just very tedious and could be very complicated to do. So one of the things that mathematicians did to try to help that, or kind of help the common folk, so to speak, is they standardized the normal distribution. Remember, we've said it could be any value you want for the mean and any value you want for the standard deviation except 0, and you could have that in any combination. So they kind of created a standard to which they could compare everything else. And that standard, they used a mean of 0 and a standard deviation of 1. They used the smallest possible values they could for the two parameters, which made the calculations a little bit easier. And to do that, they created a table. Somebody sat and did all the calculus work, and they made this lovely little table. I'm just going to show it to you so you can say you've seen it. I don't know very many people in this day and age that actually use it. One of the challenges that you have with these tables is they can be set up differently. This particular table shows me a picture and indicates that we're finding the area to the left of the z value. There are other tables that read from the middle or from the center outward. And so you have to kind of know which table you have and how to read the table. This one is for negative z-scores. There'd be a separate table for positive z-scores. And guys, this is how Miss Ralston learned it. Okay, I learned it having to use a table. I didn't have the advantage of using using a calculator or Minitab to help me with that. So you guys are really, really, really blessed in that we do have the technology now that will do it for us, and it makes the calculations so much easier so that we can focus on the interpretation. What does that tell us? And guys, honestly, that's what statistics is all about, is what do the numbers tell us? And in most cases today, guys, we do not spend a lot of time number crunching like they did way back when in, quote, the olden days, because we have the technology that will do the number crunching for us. We are going to learn how to use Minitab to calculate the stuff related to the normal distribution. We are not going to do it by hand at all. So there are really kind of two different ways that questions are presented in relationship to the normal distribution. The first one is you may see questions that say, find the area under the curve, or find the percentage, or find the probability that. Okay, and so there's one process for that, and then there's another procedure where you actually again start out knowing that percentage and have to work your way backwards to the corresponding X value. I'm hoping, and I don't know what time it is, but I'm hoping we can talk a little bit about this normal distribution today. And if need be, we will finish it on Thursday and then also get into what is termed the inverse normal distribution. Okay, so do you have questions to this point? Again, the normal distribution, excuse me, is one of the most important probability distributions that you will ever see in statistics. You can actually model a binomial distribution using a normal. You can also do an exponential so we can sometimes, if I don't have so I can kind of force it to be a normal distribution. Okay, so just be aware of that. So let's kind of dive in. Couple of things. Remember that the probability corresponds to the area under the curve. That was one of the first things that we talked about in relationship to the continuous probability distribution. Again, it is extremely important that you read the scenario from beginning to end. In these problems, you should be told that it's normally distributed. you should be told the population mean, and you should be told the population standard deviation. If you don't know those three things, you cannot work the problem. You have to know it's normal, you have to know the mean, and you have to know the standard deviation. Again, I encourage you to draw the picture of the scenario. It doesn't have to be anything to scale, but again, it helps you to decide which type you have. And there are basically, really, there are four types that Minitab addresses. You have what we call a right tail, what you call a left tail, a between, and an outside. And we'll talk about those as we go. I've given you the Minitab instructions here. Also, as a reminder, and I don't know if I've showed you this before either, but also in the course, under the content, I've added the Minitab instructions. Okay, so there is a folder under content labeled Minitab instructions. I have them sorted by modules. So we're now in module 2, and it has the Minitab instructions for the normal distributions. Okay, so they're available in D2L. They're also here on this PowerPoint, which is slide 12. One other side note, remember that we're finding an area. That area corresponds to a probability, and probabilities are never, ever negative. Now, you may have a Z value, okay, or an X value that's negative, okay, but that simply implies that you're below the mean. Okay, so just be careful about that. The area corresponds to a probability, and probability is always and forever positive. Okay, so let's take a look. I've got about 8 minutes. We'll see how far we can get. This says, according to the American College Test, ACT, results from the 2022 ACT testing found that students had a mean score of 21.524, with a standard deviation of 2.419. Assuming that the scores are normally distributed, find the probability that a randomly selected student has a reading score, has an ACT score greater than 26. It's not just reading, it's an ACT score, sorry. Okay, now, a couple of things to notice. First, it clearly tells you in the problem that is normally distributed. It clearly tells you the mean, and it clearly tells you the standard deviation. Now, just as a side note, if you were to see this written in symbols, this would say that the variable X approximates a normal distribution with a mean of 21.524 and a standard deviation of 2.419. So I have all the information I need that allows me to work the problem because I know it's normal, I know the mean, and I know the standard deviation. Okay, so again, I'm going to sketch this out. So I start out with my horizontal axis and my normal bell-shaped distribution, and the mean, always label where the mean is. The mean is the measure of center, and it is 21.524. The value that I'm interested in, it says, has an ACT score greater than 26. Okay, guys, use a little bit of common sense, not to be ugly, but if the mean is 21.524, 26 is going to be to the right because 26 is greater than that mean value. And then it says I want to be greater than 26. To be greater than 26, I'm going to be to the right. So I'm actually looking for this shaded region out here on the end of the graph. Notice that I'm in the end and it's on the right hand side. We call this a right tail. Typically, anytime you see a greater than, it's going to be a right tail because values that are greater are to the right. And again, I'm at the end of the curve. And again, we call that the tail. All right. I'm going out to Minitab now to do the calculations. Okay, so we go to Minitab. And again, if you need to see the instructions for that, they're on the slide previously. Okay, so we go out to Minitab. And I had it loaded up, but I waited too long to use it. Okay, so I've got Minitab open. I don't have to enter anything in the spreadsheet. I simply go up to my command, graph, probability distribution plot, near the bottom of the list. And I want to view probability. Okay, I'm doing one curve and I want to view the probability. So I choose view probability and I click OK. My distribution is normal. We're clearly told that in the problem. The mean is 21.524. We're told that in the problem. My standard deviation, I don't remember, but I was told it in the problem. My standard deviation is 2.419. Then we click on options. I've got all my setup. I've told it it's normal. I've given it the mean. I've given it the standard deviation. I'm going to click on options. My shaded area corresponds to a specified X value because I was given the value of 26, which is an X value. We decided it was a right tail, so I'm choosing right tail. And I have to tell it the value that I was given, 26. And I click OK, OK. And in the top, I get this nice graph, and I'm going to copy it over to a piece of paper so we can look at it and I can talk about it. Ma'am, I'm almost done. I got 2 minutes. Okay, so here's the graph that appears in the top half of the screen. It's called a distribution plot. It indicates that it's normal with a mean of 21.524 and a standard deviation. Okay, notice it has your mean labeled. It has our point of interest, which was 26. What I'm looking for, my answer, is this value right here. This is the area, this red shaded region. This is the area under the curve. Minitab has taken that crazy formula, done the calculus, and is given us this value. Okay, so 0.032. So this shaded region is 0.03213. And again, typically these are rounded to 4 places. So if I round to 4 places, this is 0.0321. So there is approximately a 3% chance that a student would score greater than 26 on the ACT in 2022. Now, I only have a minute left, so I don't have time to do additional examples. We will pick up this discussion about normal distribution and do inverse normal on Thursday. Okay, so before we go, do you have questions? At this point, you are able to do quiz 3, which is due on Sunday, because it does not have normal on it. The normal distribution is quiz 4. Okay, so you should be